Okay, so last time we looked at the hash function, college resistance hash. Resistant hash function. So from today, we'll learn about the message authentication code, or for the message integrity part. Okay. We learn about the encryption and decryption. Encryption and decryption. So in this case, the purpose of encryption and decryption is we want to hide data, right? So we want to hide the data. But now, from this part, what we are trying to do is we want to provide integrity. So attacker cannot change the data. Okay, so if attacker try to change the data, we can detect. So the goal of this chapter is about the integrity. Okay, this part is not providing the confidentiality. Confidentiality means it is through the encryption and decryption. Okay, so integrity and confidentiality are most important feature in the crypto systems. Okay, so we already covered the confidentiality. Now we are looking at the integrity part. Okay. So somebody trying to change the binary on the disk, or somebody is changing some advertisement on the website, or changing the website. Okay. So what we are looking at is we will learn about the MAC. So which is standing for message authentication code. Okay. So maybe you heard about the MAC from the digital communication or computer communication, computer network. In that class, the MAC is representing medium access code, maybe like that. But the MAC is different from in crypto system, okay? So in our class, MAC is representing message authentication code. So the meaning of MAC here is there is Alice and there's Bob. Alice is trying to send a message. Send a message. But if Alice just sending the message, then between the transferring, others can change the message, right? So to protect the change of message, Alice is adding some tag. Okay, so it's adding the tag. So Alice is generating the tag using some algorithm for this message with some key. Okay, so using the key, Alice is generating the tag. Bob is verify the message using the tag with key K. So it's a shared key because currently we are looking at the shared key system, okay, symmetric key system. So Bob and Alice has the same key value, and Alice is generating some tag using the key, and Bob is checking the tag and message whether they are matching. So this is yes or not. Okay, so this is verify algorithm. And this S is actually sign algorithm. Okay, so only someone who holds the key can generate the tag value. Okay, so it is symmetric. Symmetric. Okay. Okay. It's very similar to the encryption and decryption. Encryption case, it is using the key K. Decryption is also using the same key, right? So similarly, sign algorithm using the key K and verification algorithm also using the key K. Then we are defining the MAC algorithm, MAC system. MAC has including, so MAC is including two algorithms, sign algorithm and verification algorithm. Verify algorithm defined over. So for the sign algorithm, we need sign, key, and message. Then it's generating the tag. So key space, message space, and tag space. So sign and verification algorithm is a pair of algorithm. So what sign algorithm is doing is, sign algorithm will provide the key K message, then is generating the tag. Okay. Verification algorithm, key, message, tag, then it is returning yes or no. So the MAC, we need creating the sign algorithm and verification algorithm. Then maybe you are simply thinking about what about using error correction code or error detection code for the MAC? Error correction code or error detection code is used. Is it okay or not? Okay. So for instance, let's think about the even penalty. So even penalty means that for the given bit, the total number of one should be even number. So Alice is sending the message like 1000. Then the tag value is 1 bit, which will be 1, because number of 1 should be even number. That is even penalty. Okay. So Alice is just generating the tag using even penalty. So in this case, there is no key, right? So penalty generation, we don't need any key value. So everybody can generate the tag. Then Bob is checking message and tag. Okay. The algorithm is like this. For each message, is dividing the bit stream, and then is XORed everything using the tag, which is 0 or not. So it's checking number of 1 is even number or not. Okay. So then it is a MAC or not. So then we can ask, can an attacker modify the message with recomputing tag T? Is it possible? So attacker can change the message and recomputing the tag. Is attacker can do that? What do you think about it? Attacker can generate the tag if we are using the MAC as a error correction. Yes, right? Because if attacker is choosing the random message, new message, then attacker is just simply learning even penalty algorithm. Even parity algorithm is already known. There is no key value, so everybody can compute it. Then attacker is just sending M prime and T prime to the Bob. Then Bob is running verification algorithm. Then definitely it will be true. Yes. Okay. So anyone, even including the attacker, can generate the new tag for the new message. So error correction code or error detection code are not for Mac. Okay. Okay. So the alarm is off now. Okay. So error correction code and error detection codes are not for the Mac algorithm. These error correction and error detections are for random error. Random error case. Okay. Okay, so then what we have to do is we have to define secure MAC. So what is secure? Okay, so we have defined the secure MAC. So then we have to define the two things. What is power of the attacker and what's the goal of attacker? So adversary or attacker's power. Okay. So we are assuming that attacker power is attacker can choose any message, M1, M2, MQ. So attacker is choosing this message, then attacker can get the tag value corresponding each message. Okay, so attacker has these two things. So attacker has these pairs M1, T1, M2, T2, MQ, TQ. Okay, for any message. So what attacker can do is attacker can get some tag value for some message without knowing the key value. Okay, so anyway, attacker can get some tag value for a given message. Then, so by looking at this message pair and tag pair, attacker goal is generating the new message tag pair. New message and tag pair, which is unseen. It's not belonging to M1, T1. So unseen pair of message and tag value, attacker can generate it, new message, new tag value, then that's the success of attacker. Okay, so attacker can generate a valid, a new valid message tag pair, then attacker is succeeding. Okay, so for instance, M1, message 1 is like a hello, and tag is like 1, 2, 3, 4. M2 is word. Tag is like a 5, 6, 7, 8. And message 3 is like a best. Tag is like 1, 2, 3, 8. Okay, so attacker knows these pairs with this information. If attacker can generate new message and tag, which is like a good. Okay, so then attacker is succeeding to break this MAC algorithm, MAC things. What about the attacker can generating this pair, which is hello, is there already, but their tag is different. Then it is successful thing or not? What do you think about it? For a new is the message is already existing, okay? But attacker can generate a new tag for the existing message. Then attacker is successful to break the system. What do you think about it? In the definition of security of the MAC, Yeah, it is successful for attacker to break the system. So even for the existing message, attacker can compute new tag. Then this is not existing one, right? This is different from M1 T1. So this is not belonging. Okay, so attacker can either generating the new message and new tag, or attacker can generate for the same message but different tag. Then attacker score is satisfied. Attacker is successful to break the system. So which means that secure MAC case is not possible to generate the new tag even for the existing message. Okay. So if I'm drawing the game, secure MAC, so there is challenger and there is adversary. Okay. Then others can ask tag value for message. And challenger is returning tag value for this message. Okay. So challenger is generating the tag for each message. Okay. Then adversary is generating the new message tag pair, which is not the existing pair. Then, and also challenger checking the message and tag pair, which is really yes. Then B is 1. Otherwise, B equal 0. Okay, so we are defining this. And then we are defining advantage. MAC I, which is sign and verification algorithm, is secure. MAC if for all efficient algorithm adversary A, advantage algorithm for this A over I, probability challenger outputs 1. Their probability is negligible. So challenger can accept the valid message in tag, which is generated by attacker. So that that probability for attacker to break the system is negligible, then we are saying that the MAC is secure. Okay. So that's the definition of secure MAC. So let's look at the example then. So I sign verification algorithm is MAC. Suppose an attacker is able to find M0, M1, which are different, such that the signing of M0 and signing of M1s are equal. Okay, so attacker doesn't know about the K, but anyway, attacker can find two messages of which tag values are equal with half probability. Okay, so in this case, this MAC is secure or not? So what is the answer, do you think? So what will be the answer? It will be why? What's the advantage in this case then? So there is challenger and there is attacker. So what attacker first doing? Attacker is asking about the tag message for the M0. Okay, so then it will be tag is given, which is signing of M0. Okay, then attacker is saying that, okay, I am generating the new pair, which is M1 and T0. Okay. So with half probability, M0 and M1 has the same tag value. All right. So definitely M0, T0 is different from M1, T0, right? Because unless one bit are different, then two strings are different. So it's different. One of the accept verification is passed. That is depending on the key, right? So with half probability, this is successful. Right? So that is assumption here. For the half key case, two tag values are equal for this M0 and M1. Right? Attacker can find that message. So advantage is just half. Okay. So be aware that definitely there are two messages, M0, M1 has the same tag. That is always happening. But finding this message generally very difficult in the secure MAC. Okay. So finding the M0, M1 should be difficult. Okay, so then let's look at another one. Suppose signing algorithm K, M is always 5-bit long. So tag size is 5-bit. Tag size is 5-bit. Is it secure or not? So what's the answer? The answer will be 1. What's the advantage? So tag value is just 5-bit, which means that 5 is 2 to the 5 is 32. So attacker is just giving any message with random bit, then with 1/32, this is correct, right? Because the case of a tag is only 32 cases. So the advantage is 1/32. So this is non-negligible. Okay, so this is insecure. So that means, what about this tag size? The tag size should be long enough, right? Large enough. So this tag size is totally correlated to the security. So this tag size and this should be 128-bit. Okay, then to the so randomly the tag is chosen, then the attacker can succeed with 1/2 to the 128. So this is a very small value. So that means there is Alice. Alice is sending 1-bit message. So message size is 1-bit. What about the tag size? Tag size should be 128-bit. Okay, so even the message size is very small, tag should not be smaller than 128, even for the small message. Okay. So this MAC can be used to protect the system files, because if somebody is trying to change the system file, like a hacker is trying to change the operating system, then we have to detect it. So in order to do that, there is a file, then using the signing algorithm with the key value is generating the tag value. So for each file, tag is generated, and then if K is not there, then attacker cannot generate the new tag if attacker is changing the file content. Okay, so this approach is used for the protecting the file system from the hacking. Okay, so then let's look at how we can make a MAC algorithm based on the we learned. So we learned about the pseudo-random generator, pseudo-random permutation, pseudo-random function, right? We learn about these things. For the pseudo-random permutation function, there are AES, right? So it's a candidate for the pseudo-random function. So using this AES or pseudo-random function, how we can make a MAC algorithm, secure MAC algorithm. So using this AES pseudo-random function, let's try to make a MAC algorithm. So in the previous, using the AES, we can do the encryption and decryption. Now we are also making the MAC algorithm. Okay. So let's look at this secure MAC. Okay. So what we'll show is if we have a secure PRF, random function F, that means key is given and domain message as given, then output is given. So that is secure. Then using this PRF, we can make a secure MAC, which is sign and verify algorithm. So how we can make a sign algorithm and verify algorithm using this PRF? Sign algorithm using key message. So what do? We are just simply learning the PRF. That's all. So that is set as tag. Okay, it's very simple, right? We are just applying the PRF or AES for the message using the key value. Verify algorithm. How we can do? We are just checking. Tag is equal to. Okay. That's all. It's very naive, right? We are just applying the AES and verify case. We also computing the AES and comparing the tag is equivalent to the computation of AES. So Alice has a key K, then Alice is generating tag using like a random function using this K. Then there is a message and tag. So tag size is similar to the message, right? There's Bob. So Bob is checking, tag is equal to notation, random function, and message. Okay. So even we didn't prove this is a really secure MAC, but we will show that. So we are making this kind of MAC, even though we are not sure. So let's look at some example. There is secure PRF F, and the output size is just 10 bit. Okay, output is 10 bit. What about the derived MAC? So which means that MAC is just using this PRF. Is it secure or not? Or it depends. What's the answer? What's the answer? Yeah, it is insecure. What's the advantage? If attacker is randomly generating the tag, then it's only 10 bit, so 1/1024 probability it is successful. So 1/1000 is non-negligible, so it's insecure. So definitely the Y should be 120 bit at least. Okay. So theorem here, F is a secure PRF and the 1/Y. So Y size is very large, like a 128 bit. So 1/Y is negligible, then the MAC derived from this F is secure. Okay, so should the function is secure and also the output is large, then the MAC algorithm is secure. Actually, the advantage is like this. Advantage attacker over IF is advantage of PRF advantage plus randomly is chosen in the case 1/y. Okay. So both advantage of student and function and also of size should be negligible. Then neg is negligible. How we can prove? Just think about the function f is really random function. Okay, so small f is really random. Then what is happening? Order 3 is first choosing some message and then asking for the tag T1, T2, and TQ. So this message, this tag, it looks like what? These are just random, right? Because function f is random. So everything is random, right? So everything is random. And then for unknown message m and t is given. Then challenger is checking whether t is equal to fm, right? So for this message, given message m, given tag t, is checking tag is equal to the fm. But what we said, small f is random, right? So we didn't see that. So this is random. So random value is equal to the random value. Then what's the probability of that? So there are y cases. So these two are equal. So tag size is 1/, tag size is y, right? Like 200, 2 to the 128 cases. So by extent, these two values are equal. That is 1/2 to the 1. So 1/y. Okay. So the function f is really random case. Then the probability of attacker on this MAC is successful is 1/y. Okay, f is a random function, but f is not random. Then with the probability of PRF, we have more probability. Okay, so advantage is really increased by the PRF advantage. Okay, so then what we are doing is AS case, AS. So the previous MAC case, it is just simply signing algorithm is just PRF apply the message. But AS case, the message size is 128 bit, right? Block cipher, because it's block cipher, 128 bit. If message size is longer than 128 bit, what do we have to do? So the message is large. In that case, how we can generate the tag? So that is question. So we'll look at the two things. One is CBC MAC. So we learned the CBC mode, right? Last time we learned the CBC mode. CBC MAC is similar to that CBC mode. And another will be HMAC. Here H means is hash MAC. So hash is reducing the input size. So applying the hash, we can reduce the size of input value. So both schemes are reducing the input size to the smaller one. Truncating MAC based on PRF. So PRF case, PRF is generating some output, but for the MAC, so we are applying the MAC, then it is generating the M bit. So for instance, PRF is generating the 1024 bit. We don't need this large size bit, right, for the tag. For the tag, we just need 128 bit. So that means even f function is generating 1024 bit, some block cipher or PRF generates 128 bit, we just need 128 bit. So we are just remove the later part, truncate. So then it is secure. We are only using the 128 bit only. It is secure. Yeah, it is secure. So truncate. The function f is generating the some bit string, large bit string, but among them we are just taking this part only. That's okay. Okay. Still, advantage is the PRF advantage plus output y. So output y is here in this case truncated size. Like a W then, that is convert to the W. Okay, so then let's look at the CBC Mac. Okay, so we learn about the CBC Mac, and then we learn about the HMAC. Okay, so as I mentioned, signing algorithm is just applying the PRF. That's all. Okay, so for the PRF, we can use like AES. So our goal is for the message is very long. It's a very large message. Then we just need to small tag. So how we can do that? Okay, so message is very large, M bit, more than M bit. Okay, so if input is 128 bit, output is 128 bit, input is 1000 bit, still output is 128 bit. That's our purpose. Okay, so first we will look at the CBC Mac. So let's think about the CBC. How CBC looks like. So CBC case, message 0, so 0 message block, 1 block. So message can be divided into the blocks. Okay. CBC case, if we are using the deterministic CBC mode, we are applying the some function. When the encryption is permutation, now it is okay to use function f, then it's generating some output. Cipher case, encryption case, this is used, and then the output is going back to the next one and apply the XOR, and then should random permutation. Okay, so this one looks like a CBC, right? So every output is actually ciphertext. In the NAC case, we don't need this ciphertext. We are not using this ciphertext. We are just looking at the last one, okay? Because the last one is already contained all the message, M0, M1, old blocks, M1, M0, M1, M2, M3. Okay, so for this one, you may be thinking that this is tag, right? CBC case is not. There is another function and different key. So key is different. Different key is applied, and this is tag. So this is another one. Another one is required. So this is called CBC MAC, but last part is there, right? So last part is kind of encryption. So it is called encrypted CBC MAC. Okay. So the left part is just like a CBC, and for the last one, we are applying the new pseudo-random function with different key value. So then maybe you are asking, if this is not there, what is happening? If this is not there, so let's say this is tag, then is it secure or not, right? So you may be wondering. So if this algorithm is given, then can an attacker generate a new valid tag for new message? So if this is given, can you generate the tag value for a new message? Maybe you're wondering, right? So what I am doing is, okay, so there's challenger, there's adversary. What this is doing is, adversary is asking about the tag value for the M0 message. So M0 is one block. M0. So it's receiving the tag. And then adversary is asking about the message 0. And it's getting T0. Okay. So then what adversary can do that is, adversary can generate M0 with 0 message, and it can generate some tag. Actually, it's not T. Can generate the M0 with T, then T0. So let's look at why this is working. Okay. M0 is given. Then the tag is F is given. So this is tag. It's correct, right? If 0 is given, and the tag is T0, right? Because that's the definition of a CBC MAC, right? If the message size is a block, so only single message, single block message. And then the message is M0 and T. Let's think about it. Then function f is applied. Then what's the output of fkm0? What is value? Yeah, this is t. Okay. So this t is going back to the next block. So then what's the output of this XOR? What's the output of XOR? That is a 0. Okay. So we are applying the f. Then fk comma 0, that is what? That is t0. Okay. So for message m0 with t, tag is t0. Right? So even attacker doesn't know about the key value, but existing tag for m0 and 0 message, attacker can generate the tag for a new message. Right? m0 with t, the tag is t0. So this is valid one. It's valid, but it's not belonging to m0t or 0, t0. Totally different. Okay, so attacker can generate the new valid pair. So just simply generating the tag, this is insecure. Okay, so that's the reason why we need the last part. Without the last part, the scheme is not secure. Okay, let's get the MAC, nested MAC. So message block M0. M1, M2, M3. Then key is given. What do we do? So function f, we are providing this key as k as a key, and message is m0. Okay. Then output is key for the next block, and this is a message. And output is on next block key, and output is next block key. And there is tag. Some value is coming out. Then maybe you want to see that, okay, this is tag, but as I mentioned, if this is just last, then is insecure, okay, because attacker can generate another one. So after that one, the algorithm is adding some constant value. So fpad is constant, it's already fixed. So it's making some input value and then applied function f with another key. Okay, so we need two keys, k and k1, two key, and then it's applied. Then this is tag, is the final tag. Okay, so CBC mode or encrypted CBC MAC, simply eCBC mode, eCBC MAC, and this MMAC, nested MAC, both has the last part to avoid the attacker is generating the new tag. Okay. So let's look at this case, this example. Why the last inclusion, last part, is existing in the 22시맥 and Mmag. So what is the answer, do you think? So ECBC case, there is last part, right? This last part. And CBC also has the last part. So why do we need this last part? If last part is not there, then yeah, the mag is broken, right? Mag is forged. Forged means new tag and message are generated. So how many times do we have to query? So other words, how many times query to break the CBC mag? In case, others can ask M0 message and 0 message, right? After asking these two messages, then adversary can generate the new message tag pair. So with two message query, mag is forged. Okay. So last step is not there, then it can be forged with the two message query. Okay, so we are skipping this part. Let's go to the comparison. Okay, ECBC mag, encrypted CBC mag, is commonly used as AES-based mag. Okay, so for the pseudo random function, we are using the AES. Actually, this ECBC mag is standardized as CMag. Okay, so CMag is ECBC mag actually. So it's a standard mag algorithm. Mmag case, Mmag is not using AES or DES algorithm. The reason is Mmag case, key is given, message is given, then the output is key for the next pseudo random function. So every time different key is used, right? This key, so key is another key, another key. Key is actually updating every time. AES case, if key is changing, then it takes some time to prepare the key structure. So it takes more time for a new key value. So ECBC case, we are using the same key with the AES. In that case, we can reduce some computation. So if we are making the key constant, then it's much little faster. Okay, so if we are comparing Mmag with ECBC mag, ECBC mag is faster than Mmag. So because of this performance reason, Mmag is not going to be so popularly used. Okay, but actually this Mmag is basis of the HMag. Okay, so we currently ECBC mag or CMag or HMag is always used. Okay, so HMag is popularly used for the Mac. So next time we'll look at this ECBC mag a little bit more than HMag. Okay, then I think okay. So next time we will continue about this mag algorithm. Any question? Okay, no more question. Okay. So see you next week. Bye.